something exploded over Massachusetts, and for several hours nobody could explain what it was. It began with a sudden flash that lit up the sky so brightly that people across multiple states stopped what they were doing and looked up. Security cameras captured it. Dashcams recorded it. Thousands of witnesses reported seeing what appeared to be a blazing object streaking through the atmosphere before a powerful boom echoed across the region. Almost immediately, theories flooded social media. Some believed it was a meteor. Others were convinced it was space debris falling back to Earth. A few even suggested secret military activity or something far more mysterious. As confusion spread, scientists started collecting data from satellites, radar systems, weather sensors, and ground observations. The goal was simple: determine exactly what exploded over Massachusetts and whether the public had any reason to be concerned. But as investigators began piecing together the evidence, the story became far more fascinating than anyone expected. Because this wasn't just about a bright flash in the sky. The object's speed, trajectory, altitude, and explosive energy revealed clues about a journey that may have begun millions of miles from Earth long before a single witness ever looked up. And when NASA finally analyzed the data, the answer raised new questions about what is constantly entering our atmosphere without most people ever noticing. So what really exploded over Massachusetts? How powerful was the blast? Why was it visible across such a large area? And what did scientists discover that surprised even experienced researchers? Today, we're breaking down the eyewitness reports, the satellite evidence, NASA's investigation, and the incredible truth behind one of the most talked about sky events of the year. On what seemed like an ordinary evening in Massachusetts, thousands of people were going about their normal routines when something unexpected happened high above the region. For most residents, the night began like any other. Traffic moved steadily along highways. Families relaxed at home after work. Others were outside enjoying the evening. Nothing suggested that within moments, people across multiple states would witness an event so unusual that it would dominate social media, local news, and scientific discussions for days. Then the sky suddenly lit up. Witnesses described seeing an intensely bright object racing across the atmosphere. Some compared it to a giant firework. Others said it looked like a glowing ball of fire tearing through the darkness. Several observers reported that the object appeared far brighter than any ordinary shooting star they had ever seen. The brightness alone was enough to grab attention. But then came the sound. Minutes after the flash appeared, reports of a powerful boom began spreading throughout the region. Residents described hearing what sounded like an explosion. Some thought a transformer had blown nearby. Others believed thunder had struck unexpectedly. A few initially feared an accident had occurred close to their homes. Emergency services began receiving calls from concerned citizens seeking answers. What exactly had happened? Nobody seemed to know. Within minutes, social media platforms filled with videos, photographs, and eyewitness accounts. People from Massachusetts, Connecticut, Rhode Island, New Hampshire, and neighboring areas started sharing remarkably similar stories. Many witnesses reported seeing a bright streak moving rapidly across the sky. Others described a flash that illuminated the horizon. Some claimed they felt vibrations shortly after hearing the boom. As more reports appeared online, it became clear that this was not an isolated observation. Whatever had happened had been visible across a vast area. Local news stations quickly picked up the story. Journalists contacted emergency management agencies seeking information. Reporters interviewed witnesses who described the event in vivid detail. Video clips began circulating rapidly across television broadcasts and online platforms. Yet despite the growing attention, reliable answers remained scarce. The lack of information created the perfect environment for speculation. Some people immediately suggested that a meteor had entered Earth's atmosphere. Others argued that it could not have been a meteor because the explosion sounded too powerful. A number of users proposed that the object might have been space debris falling from orbit. More dramatic theories soon followed. Claims involving secret military projects, classified aircraft, and unidentified flying objects started spreading across social media. While there was little evidence supporting these ideas, uncertainty encouraged people to fill the information gap with their own explanations. This reaction was not unusual. Throughout history, unexpected events in the sky have often generated confusion and speculation before scientific investigations provided answers. Human beings naturally seek explanations for unfamiliar phenomena, especially when those phenomena appear suddenly and dramatically. As discussions intensified, scientists began examining available data. Astronomers reviewed observational reports. Meteor experts analyzed witness accounts. Researchers searched for radar signatures. Satellite monitoring systems were checked for unusual activity. Weather agencies reviewed atmospheric information. Every available source of evidence became important. One key challenge involved determining exactly where the object had traveled. Witness observations can be valuable, but they are not always precise. An object moving at extremely high speed across the atmosphere can appear much closer or farther away than it actually is. Perspectives vary significantly depending on location. Scientists therefore needed objective measurements. Fortunately, modern technology provides numerous tools for tracking unusual atmospheric events. Specialized monitoring networks constantly watch the skies for fireballs and meteors. Cameras positioned across different locations record bright objects entering Earth's atmosphere. Satellites monitor atmospheric activity from orbit. Radar systems detect unusual movements through the sky. Investigators knew that somewhere within these enormous datasets, the answers were waiting. As the first reports were collected, a preliminary picture began emerging. The object appeared to have entered the atmosphere at tremendous speed. Its brightness suggested an enormous release of energy. The delayed boom reported by witnesses hinted that the event had occurred high above the ground rather than near the surface. Each new clue narrowed the possibilities. Yet one question continued to dominate public discussion. If this was truly a meteor, how large was it? The answer mattered because size directly affects the amount of energy released during atmospheric entry. Even relatively small space rocks can produce spectacular fireballs when traveling at cosmic speeds. Scientists understood this well. A small object moving tens of thousands of miles per hour can generate enough energy to create a brilliant flash visible across entire regions. Still, nobody wanted to jump to conclusions. The evidence had to be analyzed carefully. Meanwhile, public interest continued growing. Videos accumulated millions of views. News coverage expanded. Experts appeared on television discussing potential explanations. And as more data arrived, investigators realized they were dealing with one of the most significant sky events seen over the northeastern United States in recent memory. What had started as a mysterious flash in the night sky was rapidly becoming a major scientific investigation. And the deeper researchers looked into the evidence, the more extraordinary the story became. As reports continued pouring in from across Massachusetts and neighboring states, one thing became increasingly clear. People desperately wanted answers. The problem was that answers were in short supply. In the hours immediately following the mysterious explosion in the sky, nobody could say with certainty what had happened. Witnesses had seen a brilliant flash. Many had heard a loud boom. Some had captured videos, while others only caught a glimpse before the object disappeared. The lack of immediate information created a vacuum. And whenever a major unexplained event occurs, speculation rushes in to fill that vacuum. Within minutes, social media platforms were flooded with theories. Some were reasonable. Others were far more extraordinary. The most common explanation was that the object had been a meteor. At first glance, this theory seemed to make sense. Meteors regularly enter Earth's atmosphere. Most burn up harmlessly before reaching the ground. Occasionally, larger objects produce bright fireballs visible across wide regions. Many witnesses immediately pointed to this possibility. After all, the object appeared extremely bright and moved rapidly across the sky. Those characteristics matched what scientists would expect from a large meteor entering the atmosphere. But not everyone was convinced. Several observers argued that the explosion seemed too powerful. Others questioned whether a meteor could really create a boom heard across multiple communities. As these debates spread online, alternative theories began emerging. One popular suggestion involved space debris. Every year, old satellites, rocket stages, and other human-made objects re-enter Earth's atmosphere. Most disintegrate before reaching the surface, but some create spectacular displays during their final descent. Supporters of this theory believe the object might have been an abandoned piece of spacecraft returning to Earth. The idea sounded plausible. After all, thousands of satellites currently orbit Earth, and many eventually fall back into the atmosphere. Some viewers even searched online databases attempting to identify recently decommissioned spacecraft that might have been passing overhead. However, there was a problem. Tracking organizations continuously monitor large pieces of orbital debris. If a known satellite had re-entered over Massachusetts, experts would likely have detected it. At least initially, no such confirmation appeared. That uncertainty allowed even more theories to emerge. Some people wondered whether the object could have been related to military activity. The northeastern United States contains numerous military installations and training areas. Whenever unusual aerial events occur, speculation about military involvement often follows. Social media users suggested everything from experimental aircraft to missile testing. Others proposed classified aerospace projects. Yet there was little evidence supporting these claims. Still, uncertainty kept the rumors alive. Then came perhaps the most predictable theory of all: unidentified flying objects. For decades, unexplained lights in the sky have sparked UFO discussions. This event proved no exception. Photos showing a bright streak crossing the night sky quickly attracted attention from communities already interested in unexplained aerial phenomena. Some users claimed the object's behavior appeared unusual. Others argued that the brightness and sudden disappearance suggested something beyond conventional explanations. Professional astronomers remained skeptical. Extraordinary claims require extraordinary evidence. And so far, there was no evidence indicating anything beyond a natural or human-made object entering the atmosphere. But the public fascination continued growing. Part of the reason was psychological. Human beings are naturally drawn to mysteries. When people witness something dramatic and unexpected, they instinctively search for explanations. In the absence of verified information, imagination often fills the gaps. This pattern has repeated itself countless times throughout history. Long before modern science existed, unusual celestial events frequently inspired myths and legends. Ancient civilizations interpreted comets as omens. Unexpected eclipses were viewed as supernatural warnings. Bright fireballs crossing the sky often became part of local folklore. Today, technology has changed how information spreads, but human curiosity remains the same. The Massachusetts event demonstrated this perfectly. Millions of people suddenly found themselves trying to solve a mystery unfolding in real time. Meanwhile, scientists remained focused on evidence. Unlike social media users, researchers could not rely on speculation. They needed measurable facts. Every video, photograph, radar observation, and satellite record represented a potential clue. Experts began comparing witness accounts from different locations. This process helped establish the object's approximate path through the atmosphere. The consistency of many reports proved particularly important. Although individual observations varied, a general pattern emerged. People across a large geographic area described a bright object traveling rapidly through the sky. Many reported seeing fragmentation. Others described sudden flashes, suggesting an explosive breakup. These details were significant because they matched behaviors commonly associated with large meteors entering Earth's atmosphere. Still, investigators remained cautious. Initial impressions can sometimes be misleading. History contains numerous examples of events that appeared obvious at first, but later turned out to be something entirely different. Scientists therefore continued collecting data before reaching conclusions. As additional evidence became available, some theories began losing credibility. Certain explanations simply failed to match the available observations. Others conflicted with known tracking information. Gradually, attention shifted toward the theories most consistent with the evidence. Yet despite growing confidence among researchers, one major question remained unanswered. If this truly was a meteor, how unusual was it? Bright meteors occur regularly around the world. However, only a small percentage becomes significant enough to attract widespread public attention. Something about this event appeared different. the brightness, the widespread visibility, the powerful boom, the enormous public reaction. All of these factors suggested investigators were dealing with something more substantial than an ordinary shooting star. As scientific teams analyzed increasingly sophisticated data sources, they began uncovering details that would soon provide a much clearer picture of what had actually happened over Massachusetts. And the most important clues were not coming from eyewitnesses. They were coming from the advanced monitoring systems silently watching Earth's atmosphere from both the ground and space. Those systems had recorded the event in remarkable detail, and what they revealed would move the investigation into an entirely new phase. While the public debated theories and investigators collected eyewitness reports, another source of evidence was quietly providing a much clearer picture of what had happened over Massachusetts. High above Earth, satellites had been watching the entire event unfold. Unlike human witnesses, satellites do not become confused by darkness, distance, or perspective. Their sensors continuously monitor the atmosphere, tracking weather systems, temperature changes, cloud formations, and in some cases, sudden flashes of light produced by powerful energetic events. For scientists investigating the mysterious explosion, satellite data quickly became one of the most valuable tools available. The reason was simple. Every major atmospheric event leaves behind signatures. Some leave visible trails. Others produce thermal anomalies. Some generate shockwaves detectable by specialized instruments. The challenge was identifying exactly which signatures matched the Massachusetts event. As researchers began reviewing data collected during the incident, they noticed something important. The timing matched perfectly. Multiple monitoring systems had recorded an unusual flash occurring over the northeastern United States at approximately the same time witnesses reported seeing the object. This was a critical breakthrough. Until that moment, investigators were relying heavily on eyewitness accounts. Now, they had objective measurements. Satellite imagery revealed that the object entered the atmosphere at extremely high speed. Although the human eye saw only a brief flash, sensors recorded a sequence of events lasting several seconds. First came the initial atmospheric entry, then a rapid increase in brightness. Finally, a sudden burst of energy as the object fragmented high above the surface. To scientists, this pattern looked familiar. Large meteoroids often behave exactly this way. As they plunge through Earth's atmosphere at tremendous speeds, friction and compression generate enormous heat. The outer layers begin to vaporize, creating the brilliant glow observers see from the ground. If the object experiences enough stress, it breaks apart violently. That breakup can release an enormous amount of energy in a very short period of time. Satellite sensors appeared to capture precisely such an event. But the imagery revealed much more than a simple flash. Researchers analyzed the object's trajectory frame by frame. By combining observations from multiple sources, they could estimate its direction, altitude, and speed. Each new calculation refined their understanding. The results suggested the object had entered Earth's atmosphere on a steep path, traveling many times faster than any conventional aircraft. That finding immediately ruled out several popular theories. No airplane could move at such speeds. No ordinary atmospheric phenomenon could produce the observed characteristics. The data pointed overwhelmingly toward an object arriving from space. Scientists then turned their attention to the brightness of the event. This detail was especially important. Brightness provides clues about energy, and energy provides clues about size. The satellite observations indicated that the flash was powerful enough to be detected across a large area despite occurring high above the Earth. That suggested the object was considerably larger than the average meteor seen on a typical night. Most meteors remain invisible to all but a handful of observers. This one attracted attention across multiple states. The difference was significant. Researchers also examined infrared data collected during the event. Infrared sensors detect heat rather than visible light. These instruments often reveal details invisible to standard cameras. The thermal signature showed an intense burst of heat corresponding with the object's fragmentation. This confirmed that a tremendous amount of energy had been released within seconds. The explosion many witnesses heard was not a conventional explosion. Instead, it appeared to be the result of a phenomenon known as an airburst. An airburst occurs when a meteoroid breaks apart in the atmosphere, releasing energy faster than the surrounding air can absorb it. The result is a powerful shockwave capable of traveling great distances. That explanation aligned remarkably well with eyewitness reports. People who heard a loud boom several minutes after seeing the flash had unknowingly provided another important clue. Because sound travels far slower than light, a delay between the visual event and the boom strongly suggested the explosion occurred high above the ground. Satellite measurements supported this conclusion. Investigators estimated that the fragmentation took place tens of kilometers above Earth's surface. At that altitude, the resulting shockwave would require time to reach observers below. What seemed mysterious to witnesses made perfect sense once the physics were understood. Scientists next focused on atmospheric conditions. Weather satellites provided additional information about the environment through which the object traveled. Cloud cover was relatively limited in key observation areas. Visibility conditions were favorable. These factors helped explain why so many people successfully witnessed the event. Had thick clouds been present, the fireball might have gone largely unnoticed. Instead, millions of potential observers had a clear view of the sky. The object appeared at exactly the right place and time to generate maximum public attention. Researchers also examined whether weather conditions could have influenced the object's appearance. Atmospheric density, temperature, and humidity can affect how light propagates through the sky. While these factors played a minor role, they did not account for the extraordinary brightness observed. The energy originated from the object itself. As more data arrived, scientists became increasingly confident about their conclusions. The satellite evidence consistently supported one explanation over all others. The object was almost certainly a natural visitor from space. Yet several important questions remained unanswered. What was it made of? How large had it been before entering the atmosphere? Where had it come from? And perhaps most intriguing of all, why did this particular object produce such a dramatic display compared to countless others that enter Earth's atmosphere every year? Answering those questions would require investigators to look beyond the flash itself and examine the object's physical characteristics. Because while satellites had revealed how the event unfolded, they had not yet fully explained why it happened. And the deeper scientists dug into the data, the more fascinating the story became. By the time scientists had reviewed eyewitness reports, satellite observations, and atmospheric data, one conclusion was becoming increasingly clear. This was not an ordinary meteor sighting. Every single day, Earth is bombarded by material from space. Scientists estimate that tons of cosmic debris enter Earth's atmosphere daily. Most of these objects are tiny. Many are no larger than grains of sand. They burn up completely before anyone notices them. Even larger meteors often pass unnoticed over oceans, deserts, or remote regions. So, why did the Massachusetts event attract so much attention? The answer lies in a combination of factors that made this particular event unusually dramatic. First, there was the brightness. Most meteors appear as brief streaks of light lasting only a second or two. While impressive, they rarely attract widespread attention outside astronomy communities. The object that exploded over Massachusetts was different. Witnesses described it as brighter than anything they had ever seen in the night sky except the moon. Some observers reported that the flash briefly illuminated the landscape around them. Others claimed it was visible through windows and reflected off nearby surfaces. Such reports immediately caught the attention of experts. Brightness matters because it reflects energy. The brighter a fireball becomes, the more energy it is releasing as it tears through the atmosphere. Scientists reviewing the data concluded that the object released a substantial amount of energy during its descent. Not enough to pose a serious threat to people on the ground, but certainly enough to make it one of the most memorable sky events many witnesses had ever experienced. Then there was the duration. Ordinary meteors often appear and disappear so quickly that observers barely have time to react. This object remained visible long enough for many people to track its movement across the sky. That extra visibility dramatically increased the number of eyewitness reports. Thousands of people had time to notice the event, identify its direction, and record what they saw. Some even managed to capture video footage. The next unusual characteristic involved fragmentation. As the object plunged deeper into the atmosphere, it encountered increasing pressure. To understand why this matters, imagine placing your hand outside a moving car. As speed increases, the force of the air pushing against your hand becomes stronger. Now imagine an object traveling not at highway speeds, but at tens of thousands of miles per hour. The pressure becomes enormous. Eventually, the stress exceeds the object's structural strength. When that happens, fragmentation begins. The Massachusetts object appears to have broken apart violently during its descent. Instead of remaining intact, it shattered into multiple pieces. Each fragment generated additional heat and light. The result was a much brighter and more dramatic display than would have occurred if the object had stayed together. This breakup process also explains the powerful boom reported across the region. Many witnesses initially believed they had heard an explosion near the ground. In reality, the event occurred far above them. The sound they heard was a shock wave. When the object fragmented, energy was released so rapidly that it compressed the surrounding atmosphere. That compression created a wave of pressure moving outward through the air. Minutes later, people on the ground heard the resulting boom. This phenomenon is similar to thunder following lightning. The light arrives first because it travels at incredible speed. Sound travels much more slowly. The delay between the flash and the boom therefore became one of the strongest pieces of evidence supporting the airburst explanation. Scientists were also intrigued by the object's trajectory. Many meteors enter Earth's atmosphere at shallow angles. They skim through the upper atmosphere before burning up. Others plunge more directly toward the surface. The Massachusetts object followed a path that maximized visibility across a large geographic area. This helped explain why reports arrived from multiple states. People separated by hundreds of miles often witnessed the same event from different perspectives. That level of visibility is relatively uncommon. Location also played a major role. Had the event occurred over the Atlantic Ocean, far fewer people would have noticed it. Had it happened during daylight hours, much of the brightness would have been lost against the sun's glare. Instead, the object appeared over a densely populated region during favorable viewing conditions. Millions of potential observers had access to clear skies at exactly the right moment. The timing could hardly have been better for attracting public attention. Another factor that fascinated scientists involved the object's apparent size. Although investigators could not immediately determine exact dimensions, calculations suggested the meteoroid was significantly larger than the average shooting star. Most visible meteors originate from objects no larger than small pebbles. This one was likely much larger before entering Earth's atmosphere. Even a modest increase in size can produce a dramatic increase in brightness and energy. That is because kinetic energy rises rapidly with both mass and velocity. An object traveling at cosmic speeds carries enormous energy, even when relatively small. When that energy is released in the atmosphere, the results can be spectacular. Researchers also compared the Massachusetts event with previous fireballs recorded around the world. Several similarities emerged. Like other major fireballs, it produced an intense flash. Like other airbursts, it generated delayed sonic effects. Like other significant meteoric events, it triggered widespread public interest. Yet the combination of brightness, visibility, atmospheric conditions, and population density made this case particularly memorable. For many scientists, it represented a valuable research opportunity. Modern monitoring systems captured the event from multiple angles. Witnesses supplied thousands of observations. Cameras recorded visual evidence. Satellites documented the energy release. Rarely do researchers obtain so much information about a single atmospheric event. The more data they analyzed, the clearer the picture became. This was not a secret aircraft. It was not a missile test. It was not an unidentified spacecraft. The evidence increasingly pointed toward a natural object arriving from space and producing a remarkable airburst high above New England. Yet despite that growing certainty, investigators still faced several unanswered questions. Exactly what kind of object was it? Where in the solar system had it originated? And perhaps most importantly, What could this event teach scientists about the countless other objects that enter Earth's atmosphere every year? Those questions would lead researchers into the next phase of the investigation and uncover details that were even more surprising than the explosion itself. After days of analysis, countless eyewitness reports, and a detailed review of satellite and sensor data, investigators were finally able to answer the question that had captivated millions of people across the northeastern United States. What exactly exploded over Massachusetts? The answer was both simple and extraordinary. According to the evidence, the object was almost certainly a meteoroid, a natural piece of rocky material traveling through space before colliding with Earth's atmosphere. At first glance, that explanation might sound ordinary. After all, meteors occur every day. People see shooting stars all the time. But the reality is far more fascinating. To understand why this event attracted so much attention, it helps to understand the difference between meteoroids, meteors, and meteorites. These terms are often used interchangeably, but scientists use them very differently. A meteoroid is the object while it is still in space. A meteor is the bright streak of light produced when that object enters Earth's atmosphere. A meteorite is any surviving fragment that reaches the ground. The object over Massachusetts began its journey as a meteoroid. For countless years, perhaps millions, it traveled silently through the solar system. Long before human beings built cities, launched satellites, or even existed as a species, this small piece of cosmic debris was already moving through space. At some point, its orbit intersected Earth's. The collision became inevitable. When that moment finally arrived, the object entered the atmosphere at extraordinary speed. Scientists estimate that meteoroids commonly travel anywhere from 25,000 to more than 150,000 miles per hour relative to Earth. At those speeds, even a relatively small object carries tremendous energy. The atmosphere suddenly becomes an obstacle. Air molecules cannot move out of the way fast enough. Instead, they compress violently in front of the object. This compression generates extreme temperatures. The surrounding air begins to glow. Material on the object's surface vaporizes. Within seconds, a brilliant fireball forms. That is precisely what witnesses across Massachusetts observed. But investigators wanted to know more. What was the object actually made of? Although no immediate recovery of physical fragments was confirmed, scientists could make educated estimates based on how the object behaved during atmospheric entry. Different materials respond differently to extreme heat and pressure. Some meteoroids are composed primarily of stone. Others contain significant amounts of metal. A smaller number are fragile mixtures of dust and rock. The way the Massachusetts object fragmented provided important clues. The explosion appeared to occur at a relatively high altitude. This suggested that the object was not composed entirely of dense metallic material. A solid iron meteoroid often penetrates deeper into the atmosphere before breaking apart. The observed behavior instead pointed toward a stony meteoroid, which is the most common type found entering Earth's atmosphere. This conclusion matched what scientists know about the overall meteor population. The vast majority of meteoroids originate from asteroids. These rocky bodies orbit the sun throughout the solar system. Occasionally, collisions between asteroids send fragments drifting into new trajectories. Over time, gravitational interactions with planets alter their paths even further. Eventually, some fragments cross Earth's orbit. When that happens, atmospheric entry becomes possible. Researchers believe the Massachusetts object likely followed a similar journey. Its story may have begun in the asteroid belt located between Mars and Jupiter. That region contains millions of rocky objects ranging from tiny particles to bodies hundreds of miles across. Collisions occur regularly. Each impact produces countless fragments. Some remain in the belt. Others begin long journeys through the inner solar system. One of those fragments may ultimately have become the fireball witnessed over New England. Scientists also examined estimates of the object's original size. Determining exact dimensions is difficult without recovered fragments. However, brightness and energy measurements provide useful clues. The calculation suggested that the meteoroid was substantially larger than the tiny particles responsible for ordinary shooting stars. Before entering the atmosphere, It may have measured several feet across. That might not sound impressive. Yet at cosmic speeds, size can be deceptive. A relatively small object traveling tens of thousands of miles per hour possesses enormous kinetic energy. When released during atmospheric entry, that energy can produce flashes visible across entire states. This is exactly why witnesses reported such an intense display. The event's brightness was not merely the result of the object's size. Its velocity played an equally important role. Speed amplifies energy dramatically. Double the speed, and the energy increases far more than twofold. By the time the meteoroid encountered Earth's atmosphere, it had become an extraordinarily energetic projectile. As investigators continued refining their calculations, another interesting detail emerged. The object appears to have disintegrated almost completely. This is actually good news. When a meteoroid explodes high in the atmosphere, most of its material vaporizes before reaching the ground. The atmosphere acts as a protective shield. Without that shield, even relatively small objects would strike the surface with devastating force. Instead, Earth absorbs most incoming cosmic debris safely. The Massachusetts event demonstrated this process perfectly. Residents witnessed an impressive fireball and heard a dramatic boom. Yet there was no evidence of widespread damage. The atmosphere had done exactly what it was supposed to do. For scientists, however, the event represented much more than a spectacular light show. It provided a rare opportunity to study an object from space during one of the most violent phases of its existence. Every fireball contributes valuable information. Each one helps researchers improve models of atmospheric entry. Each one expands our understanding of near-Earth objects. And each one reminds us that Earth is constantly interacting with the wider solar system. What began as a mysterious flash over Massachusetts was now becoming a story about cosmic origins, planetary defense, and humanity's ongoing effort to understand the universe around us. But even with the object's identity becoming clearer, one mystery still remained. Several characteristics of the event appeared unusual: the brightness, the fragmentation pattern, the energy release, and the sheer amount of data collected. These details would soon attract the attention of experts around the world. Because while scientists now had a strong understanding of what the object was, they were beginning to realize that this particular fireball might be more significant than anyone initially expected. By this point in the investigation, scientists were increasingly confident that the object which exploded over Massachusetts was a meteoroid that had entered Earth's atmosphere at tremendous speed before breaking apart high above the ground. For the public, that answer seemed to solve the mystery. Case closed. A space rock entered the atmosphere, created a spectacular fireball, and exploded. But for researchers studying the event, the story was only beginning. Because as experts examined the data in greater detail, they started noticing several characteristics that made this fireball stand out from many others recorded in recent years. None of these discoveries suggested anything supernatural. None pointed towards secret technology or unidentified spacecraft. Instead, they highlighted something scientists often find even more exciting: an opportunity to learn something new. The first surprise involved the brightness of the event. Most fireballs are observed by a limited number of witnesses. Even relatively large meteors often go unnoticed if they occur over remote regions or during unfavorable conditions. The Massachusetts event was different. Reports arrived from an enormous geographic area. Observers separated by hundreds of miles described seeing the flash. Videos surfaced from multiple locations. Security cameras captured the event from different angles. For researchers, this created an unusually rich dataset. Normally, scientists must reconstruct a fireball's path using a limited number of observations. In this case, they had access to far more information than usual. Every video became a measurement. Every eyewitness account became another piece of evidence. Every recorded timestamp helped improve the reconstruction. The result was one of the most detailed analyses possible for an event of this kind. Then came another surprise. The object's fragmentation behavior appeared unusually dramatic. When meteoroids enter Earth's atmosphere, they rarely break apart in a simple manner. Some remain intact until very low altitudes. Others gradually disintegrate. A few experience multiple explosive fragmentation events during descent. The Massachusetts object appeared to undergo a particularly energetic breakup. Researchers studying the light curve, the graph showing changes in brightness over time, noticed sharp fluctuations. These variations suggested that pieces of the object were separating and releasing energy in rapid succession. Each breakup event produced additional flashes. Each flash revealed new information about the object structure. To scientists, fragmentation patterns are like fingerprints. They provide clues about composition, density, and internal strength. The Massachusetts fireball appeared less robust than a solid metallic object, yet stronger than many fragile cometary fragments. That combination immediately attracted scientific interest. Experts wanted to understand why it behaved the way it did. Another unexpected detail involved the altitude of the explosion. Initial calculations suggested that the major airburst occurred relatively high in the atmosphere. This finding raised important questions. Objects exploding at high altitudes are often less dense. Denser materials typically penetrate deeper before breaking apart. Yet the brightness observed during the event indicated a substantial release of energy. Reconciling these two facts required careful analysis. Scientists spent considerable time refining their models to determine exactly how the object interacted with the atmosphere. As they did so, they discovered that even small changes in estimated composition could significantly alter the results. This highlighted one of the challenges facing modern meteor science. Researchers rarely get to examine the original object directly. Instead, they must reconstruct its characteristics from the evidence it leaves behind. The Massachusetts event provided more evidence than most. Even so, uncertainty remained. Another aspect that caught expert attention involved the sonic reports. Thousands of witnesses described hearing booms, rumbles, or explosive sounds after seeing the flash. At first, this seemed entirely consistent with an atmospheric airburst. But the sheer number of reports helped scientists better understand how the shockwave traveled through the atmosphere. Sound propagation is influenced by many factors: temperature layers, wind patterns, humidity levels, atmospheric density. All can affect how sound moves across long distances. By comparing witness reports with atmospheric models, researchers gained valuable information about both the event and the environment through which the shockwave traveled. In effect, the fireball became a natural scientific experiment. Then investigators encountered something that often excites researchers more than clear answers: uncertainty. Several measurements did not align perfectly. Different analytical models produced slightly different estimates for speed. Some calculations suggested one range of energy release. Others suggested another. The differences were not enormous, but they were significant enough to require additional study. For the public, uncertainty can be frustrating. For scientists, it is often where discovery begins. Disagreement between models forces researchers to examine assumptions. It reveals weaknesses in existing methods. And occasionally it leads to breakthroughs. The Massachusetts event offered exactly this type of opportunity. Because the available data was so extensive, scientists could compare multiple reconstruction techniques and identify areas where improvements might be possible. Another factor that generated excitement was the event's timing. Modern observation networks have never been more advanced. High-resolution satellites continuously monitor Earth. Automated cameras scan the night sky. Radar systems collect enormous amounts of information. Computers process data at speeds unimaginable just decades ago. As a result, the Massachusetts fireball was observed using technologies unavailable during many historic events. Researchers could analyze the incident in extraordinary detail. Every sensor added another layer of understanding. Every observation strengthened the overall picture. This wealth of information transformed a brief atmospheric event into a valuable scientific resource. Perhaps most importantly, the fireball served as a reminder of how dynamic Earth's environment truly is. Many people think of space as distant and disconnected from daily life. In reality, Earth constantly interacts with material from beyond our planet. Thousands of meteoroids enter the atmosphere every day. Most are tiny. Most pass unnoticed. But occasionally, An object arrives that captures public attention and scientific interest simultaneously. The Massachusetts event was one of those rare moments. It reminded people that our planet exists within a much larger cosmic environment. It demonstrated the effectiveness of modern monitoring systems, and it provided researchers with a remarkable case study for future investigations. Yet despite all the progress made so far, one critical question still remained. What happens next? Could similar events occur again? How often do objects like this enter Earth's atmosphere? And what are scientists doing to monitor future threats from space? The answers would reveal just how closely experts watch the skies every single day, and why the next unexpected flash overhead may already be on its way. With scientists now largely agreeing on what exploded over Massachusetts, public attention began shifting toward a different question. Could it happen again? The answer, surprisingly, is yes. In fact, events like this happen far more often than most people realize. The difference is that most occur unnoticed. Some take place over remote oceans. Others happen above deserts, forests, or sparsely populated regions where few people are present to witness them. The Massachusetts fireball attracted extraordinary attention because it occurred over a heavily populated area at exactly the right time. Millions of people had an opportunity to see it. But from a scientific perspective, Earth's encounter with objects from space is an ongoing process. Every day, our planet sweeps through vast amounts of cosmic debris. Tiny particles strike the atmosphere constantly. Most are harmless. Many burn up completely before reaching lower altitudes. The spectacular streaks commonly called shooting stars are evidence of this continuous bombardment. Scientists estimate that thousands of tons of extraterrestrial material enter Earth's atmosphere every year. Fortunately, the overwhelming majority consists of microscopic particles or very small fragments. Large objects are much less common. Still, they do occur. And that is why researchers continuously monitor the skies. Modern detection systems have become remarkably sophisticated. Ground-based cameras operate throughout many parts of the world. These networks automatically scan the sky for bright fireballs. When an unusual event occurs, multiple stations often record it simultaneously. The observations are then combined to calculate speed, altitude, trajectory, and possible impact zones. In addition to ground observations, satellites play a crucial role. Some orbital systems can detect flashes produced by atmospheric explosions. Others track larger objects moving through near-Earth space. Together, these technologies provide scientists with an increasingly detailed understanding of what is happening above our heads. Yet despite these advances, important limitations remain. One of the biggest challenges involves object size. Large asteroids can often be detected months or years before they approach Earth. Smaller objects are much harder to spot. Many remain invisible until they are already entering the atmosphere. The Massachusetts object appears to have fallen into this category. It was large enough to create a spectacular fireball, but small enough to avoid widespread detection before atmospheric entry. This is not unusual. Researchers have long understood that numerous small near-Earth objects remain difficult to track. Most pose little danger. However, they still provide valuable scientific opportunities when they enter the atmosphere. Each event improves our understanding of the population of objects surrounding Earth. The Massachusetts incident also highlighted the importance of planetary defense programs. When people hear the phrase planetary defense, they often imagine giant asteroids threatening civilization. In reality, planetary defense involves much more than catastrophic scenarios. It includes monitoring near-Earth objects, improving detection technology, refining impact models, and developing strategies for responding to future events. Organizations around the world contribute to these efforts. Scientists continually search for potentially hazardous asteroids. Observatories track known objects and update their predicted paths. Engineers develop new instruments capable of detecting smaller and more distant targets. Every improvement increases humanity's ability to understand the environment around our planet. The good news is that the Massachusetts fireball did not represent a significant threat. The atmosphere performed exactly as expected. The object fragmented high above the ground and released most of its energy before reaching the surface. Events of this size are generally considered natural and manageable. Nevertheless, they serve as valuable reminders. Earth exists within a dynamic cosmic environment. Space is not empty. Countless objects travel through the solar system on complex and ever-changing trajectories. Most never come close to Earth. Some pass safely by. A few eventually intersect our planet's path. When that happens, the results can range from a brief shooting star to a dramatic airburst like the one witnessed over Massachusetts. Scientists therefore remain vigilant. Observation networks continue operating around the clock. New telescopes are being developed. Artificial intelligence is increasingly being used to identify potential objects of interest. Future monitoring systems will likely be even more capable than those available today. In many ways, the Massachusetts event demonstrated how effective modern science has become. Within a short period of time, researchers collected eyewitness reports, analyzed satellite data, reconstructed the object's trajectory, and developed a detailed understanding of what occurred. Decades ago, much of that information would have been unavailable. Today, investigators can solve mysteries in the sky with unprecedented speed and accuracy. Still, not every question has been answered. Scientists continue studying the event. Additional data may refine estimates of the object's size, composition, and origin. New analytical techniques could reveal details currently hidden within the observations. Research often continues long after public attention fades. That is one reason events like this remain valuable. They contribute to a growing body of knowledge that helps prepare humanity for future encounters with objects from space. And there will undoubtedly be future encounters. Perhaps not tomorrow. Perhaps not next week. But somewhere above Earth, another meteoroid is already traveling through the darkness of space. Eventually, its path may intersect with our planet's. When that moment arrives, scientists will once again turn to their instruments, satellites, and observation networks to understand what happened. The Massachusetts fireball may be over, but the story of Earth's ongoing relationship with the cosmos is far from finished. And that leads to an even bigger question. What does this event tell us about our place in the universe, and what lessons should we take from it moving forward? The mysterious explosion over Massachusetts may have lasted only a few seconds, but the lessons it offers extend far beyond a single night and a single fireball. For most people, the event was an unexpected spectacle. A bright flash. A loud boom. A mystery that dominated conversations for days. But for scientists, it was a reminder of something much larger. Earth is not isolated. Our planet moves through a constantly changing cosmic environment filled with dust, rocks, asteroids, and debris left over from the formation of the solar system billions of years ago. Every day, Earth encounters this material. Most of it burns harmlessly in the atmosphere. Most of it goes unnoticed. Yet every so often an object arrives that reminds us just how active our celestial neighborhood really is. The Massachusetts fireball was one of those reminders. It demonstrated the remarkable role Earth's atmosphere plays in protecting life on the surface. Without that protective layer, even relatively small objects from space could strike the ground with tremendous force. Instead, the atmosphere absorbs and disperses much of their energy high above our heads. The event also highlighted how far modern science has come. Just a few decades ago, investigators would have struggled to reconstruct an incident like this. Today, satellites monitor the planet continuously. Ground-based cameras automatically record the night sky. Radar systems track atmospheric activity. Powerful computers analyze enormous amounts of data within minutes. Because of these technologies, scientists were able to move from uncertainty to understanding with remarkable speed. The fireball also revealed the value of public participation in scientific discovery. Thousands of eyewitness reports contributed important information. Videos from security cameras, doorbell cameras, and dashboard cameras helped researchers refine their analysis. Ordinary citizens became part of the investigation. This collaboration between technology and public observation is becoming increasingly important in modern science. Looking ahead, researchers expect similar events to continue attracting attention. As monitoring systems improve, more fireballs will be detected and analyzed than ever before. New telescopes are being built. Detection networks are expanding. Artificial intelligence is helping identify unusual objects faster and more accurately. Each improvement strengthens humanity's ability to understand both small atmospheric events and larger potential threats. Perhaps the most important lesson is perspective. The Massachusetts event reminded millions of people that our world is connected to something much bigger than everyday life. Above the clouds, beyond the atmosphere, an endless cosmic environment surrounds our planet. Most of the time, we rarely think about it. Then, for a brief moment, a brilliant flash crosses the sky and reminds us that Earth is part of a much larger story, one that scientists are still working to understand. And while investigators may now know what exploded over Massachusetts, the universe continues to send new mysteries our way. The next one could arrive at any time. What began as a mysterious flash in the night sky has now become a remarkable scientific story. Thousands of people across Massachusetts and neighboring states witnessed something they could not immediately explain. A brilliant streak of light raced across the sky. Moments later, a powerful boom echoed across the region. Social media exploded with theories. News stations rushed to cover the story. And for a brief period, nobody knew exactly what had happened. But as investigators gathered evidence, the mystery slowly unraveled. Eyewitness reports provided the first clues. Satellite observations captured the event from above. Atmospheric data revealed how the object behaved during its descent. And scientific analysis ultimately pointed to the same conclusion. The object that exploded over Massachusetts was most likely a meteoroid from space that entered Earth's atmosphere at tremendous speed before breaking apart high above the ground. Yet what made this event so unusual was not simply what it was. It was how visible it became, the brightness, the shockwave, the widespread observations, the amount of data collected. Together, these factors transformed a brief cosmic encounter into one of the most talked about atmospheric events of the year. The incident also served as a powerful reminder that Earth is constantly interacting with the wider universe. Every day, our planet encounters material from space. Most of it passes unnoticed. Most of it burns harmlessly in the atmosphere. But occasionally, an object arrives that captures the attention of millions and reminds us that our world is part of something much larger. For now, scientists believe they understand what happened over Massachusetts. But research continues. Data is still being analyzed. Models are still being refined. And every new discovery helps improve our understanding of the objects moving through our cosmic neighborhood. Because while this mystery may be close to being solved, countless others remain. Somewhere in the darkness beyond Earth, new objects are already traveling through space. Most will never come near us. Some will pass safely by. And a few may eventually light up the sky just as dramatically as the one that stunned Massachusetts. The atmosphere is still changing. The skies are still full of surprises. And what happens next may not only reveal more about our planet, but also about the vast universe that surrounds it. The next flash in the sky could be tomorrow. And when it happens, scientists will be watching,